So here's the velocity time graph for the falling object, and here's the differential equation that governs the curve. And we want to solve that differential equation, which means that we want to know what v is as a function of t. Now that can't just be done by algebra because there's a rate of change, a derivative of v in the equation. As it happens, this particular differential equation requires a bit of maths that we haven't come across yet to solve. So instead we're going to solve it numerically. Now what does that mean? Well, we are going to look at a velocity at a particular time and then see how that velocity evolves by looking at the rate of change of that velocity. So at time t on this graph, we have a tangent to the curve, and the gradient of that tangent is the instantaneous acceleration. And what we're going to do is we're going to say that the velocity increase in the time interval delta t is going to be modelled as the acceleration at time t multiplied by the time interval delta t. Now in modelling it this way, what we're saying is that the red tangent curve is being assumed to be a good approximation to the blue velocity curve. And we've seen this kind of thing before, and we know that that approximation becomes better and better as we shrink delta t smaller and smaller. If we're using values of delta t that are sufficiently small for that to be a good approximation, then the velocity at a later time is going to be given by the velocity at the earlier time plus an extra bit of velocity due to the acceleration. So we're going to use that approach to find the velocity as a function of time by finding a velocity at a certain time and then adding on increments of velocity that are calculated from the acceleration. So to do that, we've inputted some parameters of our system. We're saying that the mass of the object is 60 kilograms. There's a drag coefficient here and a value of g. And we can use some basic physics to put the formulas in that will just make this all work, hopefully. So the weight is equal to the mass multiplied by g. Okay. The drag is equal to the drag coefficient multiplied by the velocity squared. Now we don't have any velocity at the moment, so that's going to come out 0. The resultant force is going to be equal to the weight minus the drag, and the acceleration from Newton's second law is going to be equal to the resultant force divided by the mass. And as this thing is falling from rest, we'll set an initial velocity to be 0. Now what we haven't yet put in is a rule for how the velocity is going to evolve. So thinking back to the previous slide, we're going to say that the velocity is equal to the previous velocity plus the acceleration multiplied by the time interval. But as we've conveniently chosen the time interval to be 1, we're okay and good to go like that. Now if we fill this down and fill these down, it'll successively recalculate, and look what we get. The curve that we were looking for all along. Now we can do some weird stuff with this. We can set the drag to be 0. If there's no drag, then we get uniform acceleration. Let's put the drag back. Notice that the terminal velocity is about 54 meters per second. Well, look what happens if we change the mass. A slightly heavier object will end up with a slightly greater terminal velocity. Now remember, this does not give an exact solution to the differential equation. That's not because there's any physics missing. There's the same amount of physics in here as there is in the differential equation. However, we're dealing with 1 second time increments here, and we might discover that those time increments don't give a sufficiently good approximation to the real solution. If that's the case, we could shrink the time intervals so that instead of stepping up by 1 second each time, we could step up by, say, 0.1 second and see what effect that has. And you might want to try that yourself.